Okay, so this is going to be our final lesson. It's looking at the bits and pieces in C13 and C14 that people were less happy with. To be honest, this kind of divides into two sections really. First bit was pretty commonly the stuff to do with writing chemical equations and writing balanced equations to describe processes for the Earth's atmosphere. And then the next bit was looking at things to do with evaluating things. So we'll look at both of those aspects. Right, it's the first statement that got a lot of red. It was using balanced simple equations to explain how gases were formed in the atmosphere and explain how oceans were formed. Right, so first up, the early atmosphere. You are expected to know what gases were about in the early atmosphere. Now I say were about, obviously this is all theoretical, so the evidence suggests that these gases were around. In terms of where they came from, this would be due to volcanic activity, mainly is what would have put them there. So why not pause this or press escape, or I don't know, do something, and see if you can actually list those gases. Okay, so you should have got water vapor, you should have got carbon dioxide, you should have got methane, and you should have got ammonia. Right, so those are the four gases. The second thing you need to be able to do is to actually write the chemical formulae for each of those four. So again, why not pause this and see if you can actually write the chemical formula for those four. Okay, so first one hopefully was pretty straightforward. Oh, hang on, no, you've done your formulae, we'll come to those in a sec. Right, what you're actually also supposed to know is the main gases in the current atmosphere. Now, AQA just says that you need to be able to know that the main two, but of course there are lots more. So the main two you should be able to name. Bit of a clue, one of them is 78%, and the other one is 21%. So see if you can write those down. Right, so those main two were oxygen 21%, nitrogen 78%. Of course, that does leave 1% that I haven't covered. That 1% is made up of carbon dioxide, water vapor, noble gases, mostly argon, other bits and pieces. But those are the two that we're going to be talking about. So as I said before, hopefully you've already written down your chemical formulae for the top four. If you haven't written down the oxygen and nitrogen chemical formulae, have a go at doing that as well, because I'm about to pop those up. Right, water vapor, I would like to think everyone knows, is H2O. Carbon dioxide, of course, is CO2, di meaning two oxygens. Methane and ammonia are a little bit less well known. So methane is the stuff that comes out of the gas taps at school, and that is CH4. It's a hydrocarbon. And ammonia is a kind of stinky, horrible substance, and it is NH3. Oxygen and nitrogen are both diatomic, so they are O2 and N2. Right, so we've now going to look at actually how these gases were formed in the atmosphere and how the oceans were formed. Now, in terms of the balanced simple equations a bit, that might be a bit misleading, I guess, because it's pretty straightforward, the first little bit. The oceans formed due to the condensation of water vapor. So condensation, of course, because as the Earth cooled, right, it cooled below 100 degrees and that water will have condensed and formed the oceans. Right, now this is going to sound a bit weird, but see if you can write an equation to show the condensation of water. Right, now if that sounds a bit tricky, all we're really looking for here is state symbols. So have a go at that. And with a bit of luck, you might have written something like this. H2O gaseous, so vapor, goes to H2O liquid, so liquid. So that would represent the condensation of water vapor. So that's one of the processes that occurred. Other things you're expected to know about is how CO2 reduced. Now there are a couple of ways, one of which was as soon as the oceans were formed due to the water vapor condensing, CO2 is soluble in water, so therefore it will dissolve. So I wonder if you could write down an equation similar to the one above, which shows carbon dioxide dissolving. So hopefully, again, this is just a state symbol situation really, and that is gaseous carbon dioxide going to a carbon dioxide solution. Right, now the next one is another reason why carbon dioxide decreased, and also why, of course, one of the other gases increased. And as you are well aware, I'm sure, the first life evolved in the oceans, and the first sort of type of life, if you like, were after the single cell stuff, was looking at plant-based life. And of course, as soon as green plants specifically evolved, then that means you could get photosynthesis, which I'm sure you all know is the formation of oxygen. Right, so obviously this was a pretty important process. This one is a slightly more complicated equation. Hopefully you've seen it before. Have a go at writing down the equation for photosynthesis now. If you can only do it as a word equation, no, that's great, but a symbol equation is what we're after, and of course the end game is going to be a balanced symbol equation, so have a go at writing that down now. And you should have written something like this. Carbon dioxide plus water makes glucose, that is what C6H12O6 is, that's glucose, type of sugar, and oxygen is the byproduct. Okay, so if you didn't get that, you could still have a go at trying to balance it, because in a second the balanced equation is going to appear underneath. So have a go at balancing that. And the balanced equation is 666. Okay, so that's a relatively straightforward one to remember. Also, I'm sure you're aware that the opposite way round, so going from glucose plus the oxygen going to the water and the CO2 is, of course, respiration. Okay, so the next statement, which was pretty similar, was it says you can use balanced symbol equations to explain how carbon dioxide formed sedimentary rock and how methane and ammonia were removed from the atmosphere. Right, so first of all, let's look at CO2. So on the previous slide, we looked at the fact that carbon dioxide will dissolve in water. Now, in actual fact, when carbon dioxide dissolves in water, it actually forms something called carbonic acid. Now, basically, the technical term for carbonic acid, the alternative chemical name would be hydrogen carbonate. So the next equation that's going to appear is carbon dioxide reacting with water to make hydrogen carbonate. Now, you might be able to have a go at writing that. Have a go. It's going to appear anyway, and then we're going to talk a little bit about it. So there you go. Water and carbon dioxide makes this thing called hydrogen carbonate or carbonic acid. Now that CO3 bit, that is what is known as a carbonate ion, and sedimentary rocks basically contain the carbonate ion. So that carbonate ion gets absorbed by things like sea creatures, and they form their seashells out of it, and then of course their shells get crushed and form things like limestone. So it's that carbonate, right, or CO3 2- ion that's the important bit there. Right, methane. Okay, now methane got removed from the atmosphere basically after there was a significant buildup of oxygen. So what I'd like you to do now is see if you can write an equation for the reaction of CH4 methane with oxygen. Now, as a little bit of a clue, we did a lot of this type of reaction in the balancing equations lesson. Right, so with a bit of luck, you might know what is formed. Okay, so hopefully you wrote something like this. So whenever you burn anything that is a hydrocarbon, hydrocarbons contain carbon and hydrogen. So whenever you burn them or whenever they oxidize, i.e. react with oxygen, right, as long as there is enough oxygen, that's called complete combustion. As long as there's enough oxygen, you will always get CO2 and water. Right, so that was your oxidation reaction of methane, and you can see it forms carbon dioxide and water vapor. Now, if you haven't done so, that needs balancing, so that's about to appear. So see if you can have a go at balancing that. And just like before, the method is number of carbons, same, don't put anything there. Hydrogens, 4 there. Basically, you need to half that number and stick it in front of here, so you put a 2 here. And then count the oxygens. And that should give you this. So that's how methane was removed. And the final one, it says ammonia, how that's removed from the atmosphere. Right, ammonia, there it is, NH3. Similar sort of process, so it needed oxygen around. So this is another oxidation reaction. So see if you can write an equation for the reaction of ammonia with oxygen. The clue here is there are 2 products, and one of them forms is one of the gases that is the majority of the current atmosphere. So see if you can write a chemical equation or even a balanced chemical equation for that process. Right, so when you react ammonia with oxygen, you make the following: water and nitrogen. Right, so if you haven't done that, or if you haven't written down that, write it down now and have a go at balancing it. Right, so to balance this one, you've got your nitrogen there, and there's 2 there. So the first thing I'd probably do is whack a 2 in front of that, because you're going to have that to get the nitrogen sorted out. So 2 there. Then, of course, that will give you 6 hydrogens. So you're going to have a 3 in front of this. Now, that might make you unhappy because you've got 3 oxygens there and 2 there. So you might want to carry on doubling things. But at this point, I would go, well, okay, if I've got 3 oxygens on the right, I'm just going to need to do 1.5 of this one. So that's what I've got written down. Now, it's perfectly fine if you wrote 4, 3, 6, 2, because remember, this thing is just a ratio, isn't it? All right, so that's your process for the oxidation of ammonia. Oh yeah, there you go. So there's the 4362 version. Right. Right, now the next statements that people were looking at were, these were in different places actually, but they were very, very similar. I can evaluate the use of products, services, or events in terms of their carbon footprint, or I can evaluate products in detail using life cycle assessments. Now, basically what I'm going to do is look at this word, because in science, the word evaluate is a prompt word, which actually means that they want you to do something specific. And the easiest way to show you this is by looking at an exam question example. So let's have a look at that on the next page. Right, so we go. Greenhouse, lovely, nice picture of a greenhouse. Could be wood or aluminium. Table 1 shows some information, lovely, there's some stats, I'm sure you can read that. Evaluate the use of each material in making greenhouse frames. Right, so whenever you see this word, right, it's going to likely to mean you're going to be doing a long answer question. I've chopped off the lines. All right, this is a long answer question, right? And what it means is you need to basically weigh up pros and cons, or look at good and bad points about each of the things that they're talking about. So in this particular case, it's wood versus aluminium, but it could be paper bags versus plastic bags, or it could be, you know, looking at the life cycle of a paper bag versus the life cycle of a plastic bag, or it could be loads of things. But what they want you to do is to weigh up the good and the bad things and then make a judgment based on that evidence. So you must write a judgment or conclusion at the end. If you do not write a judgment or a conclusion, you will not get the top marking band. Okay, so this is a banded mark scheme, and you'll see what I mean in a second. All right, doesn't matter which one of those 2 things you go for, as long as you make some kind of decision. So in this particular case, of course, you're going to be looking at, like I say, wood and aluminium. Little tip, don't just quote stuff from a table. What I mean by that is, clearly you could just write wood is renewable. It has a mass of 80 kilograms. Yeah, it has a useful lifetime of 20 years. This is just quoting facts. What you need to be doing is writing things that imply that you understand what these things mean. Yes. Wood is renewable, so it will not run out. So you can plant more trees, something like that. So just make sure it is clarified that you know why it's a good point. Right, now I'm not going to bang on too much about this because I'm going to have a look at the mark scheme, and then you're going to have a go at one yourself. So the mark scheme is on the next slide. Right, so here we go. Look at the top here. To get the top level, this was out of 4. You need a judgment, so a conclusion or a judgment that is strongly linked and logically supported by a range of reasoning. And then, of course, yeah, you can get lower marks than that. We don't want lower marks than that. So indicative content means the kind of stuff that you could chat about. So these are the things that you could talk about. However, if you just literally talk about these things, right, you will be capped at 2 out of 4 in this case because you have not made a judgment. So it's very, very important that you do that. So this is what I mean. You can't just say wood's renewable. You need to say what it means. Yeah, it's not going to run out. Yeah. Or, of course, you could quote the opposite. You wouldn't get a mark for both of those, by the way. It's one or the other. All right. It's going to be more expensive to process aluminium. Now, that's something you might not be aware of at the moment because we haven't covered that, but that is something they'll allow. The fact that this one is heavier than this one, well, that's just a fact. You can write that, but that doesn't get you any marks. You need to explain why that's an issue. So obviously, it'll be more expensive to transport it. As you can see there, you're going to need more fuel, blah, blah. You can read that. The useful lifetime, again, don't just quote the numbers. Talk about why it's better. So obviously a wooden greenhouse, you would need to replace it more. So that's obviously not why it's better, that's why it's worse. Or the opposite, you wouldn't probably get a mark for both. And then again, the fact that you can use them for other things, make it really explicit that you understand why these are good or bad things. Then, like I say, once you've done all that, you would then have to decide one or the other. It wouldn't matter which you pick. Doesn't matter. That's not the point. The point is that you actually pick one. And if you're not really sure what to go for, a standard answer to write at the end would be, I think that, I don't know, aluminium is a better material for a greenhouse because the good points outweigh the bad points, or something like that. That's absolutely fine. Right. So that's one about raw materials. Have a look at the question that I've also set. There's one on there that is about, it's another data one, and it's looking at pollutants. So see if you can have a go at that one.